Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the first video of week 12. In this video I want to prove the parts A, B and C of theorem 626. This theorem was discussed in the last video. It gives important results on the Shapley value of a cooperative game. So let us go back to these statements. So here you see the statement, the first part of the statement. So the set of players 1 to m is fixed all the time. Part A says that there is a unique map from the set of all coalition valuations to the vector space R up to m, which satisfies a certain system of 4 axioms. Namely, axiom of efficiency. The sum of the values of such a vector is equal to the valuation of the total set. Axiom 2, axiom of the dummy player. In such a vector, the entry of a dummy player for a given coalition valuation is equal to 0. Axiom 3, axiom of symmetry. If the permutation pi is an automorphism of a coalition valuation, then the entry xi I is equal to the entry xi pi of I for any coalition valuation, which also makes sense. Players which have the same properties should get the same value. And axiom 4 is axiom of additivity. It's part of linearity. The set of coalition valuations has a vector space structure, and additivity says that xi respects the sum. So xi of the sum of two coalition valuations is equal to xi of the first one plus xi of the second one. Part B gives an equivalent characterization. More precisely, here we consider another unique map, xi upper index B, which is defined by its values on the basis of the vector space of all coalition valuations and by linearity. So this is linear algebra. If we have any linear map from some vector space to some other vector space, it is unique, it is sufficient to give its values on the basis, then it extends uniquely by linearity. So here we have the axiom of linearity, which is a bit stronger than the axiom of additivity. I call it A4 prime. And we have the second axiom, A5, which gives the values on the basis. And here we choose the new basis from lemma 625 of these coalition valuations VC for C non-empty subset of A, and the value is prescribed as follows. The entries for player i's not in C are supposed to be 0, and the other entries for the player I in C are 1 over number of elements of C. So this coalition valuation has this vector has only two values, 0 or 1 over 1 divided by absolute value of C. So the claim is now that this is the second characterization of the Shapley value. More precisely, this vector xi up index B is equal to the Shapley value Shapley of the coalition valuation. So in part C, I will reformulate, reconsider when we come to it, but first I want to prove the parts A and B. So the map xi up index B is certainly well defined because it is linear and it's given by the coalition valuation, by the values on the coalition valuations in the basis of the vector space. So now we will show first that this vector satisfies the axioms A1 to A4, or that this map satisfies axioms A1 to A4, and then afterwards that it's the only map which satisfies these axioms. And these two statements prove in the parts A and the part B. So let's start. The map xi upper B satisfies the axiom A4 because it satisfies axiom A4 prime. A4 was additivity and A4 prime is stronger, it's linearity. So this is clear. Linearity implies additivity. So it satisfies the axiom A3, the axiom of symmetry, and for that we have to make some arguments and calculations. So let us be given the coalition valuation V and let this permutation pi be an automorphism of V. That means that V composed with pi is equal to V. Now we write this collision valuation as a linear combination of this new basis from lemma 625, sum over of lambda b times vb for non-empty subsets B of A. And then first we have a general statement. The composition of any collision valuation VB with a permutation is the same as the collision valuation V pi up to minus 1 of B. So this here I wrote already the reason. So the collision valuation on the left hand side takes value 1 on a collision C if pi of C contains B, and else it has value 0 on C. And the collision valuation on the right hand side has value 1 on a collision C if C contains pi up to minus 1 of B, and else it has value 0 on C. And now it's obvious that these conditions are equivalent because pi is a bijection. It's a permutation. So therefore these two collision valuations are the same, even in general. And now further, yeah. So next calculation, the collision valuation V is by this symmetry is equal to the collision valuation V composed with pi. So, and by definition, the left-hand side is this sum over lambda b times Vb, and the right-hand side is this, yeah, the sum of these compositions here. So here we have these compositions. And on the right-hand side, I can now change the sets B over which I sum. Instead of B, I can consider the sets. Oh no, I don't. This is, we had just seen that this here is equal to V pi minus 1 of B. That's what we saw on the last slide. That's the next equality here. And maybe I take this one. And now here I do now some change in the summation index, the sets B. Instead of the set B, I consider now the new B is the old pi up to minus 1 of B. And then I come here to these two new indices, lambda pi of B times VB. And now if you compare now this sum with this sum, they are equal. And so they give the same linear combination, but VB was, the set of VB is the basis. Therefore the coefficients lambda B and lambda pi of B must coincide. So now we can go on. Now I can look at the value psi I B of V. And here is written what it is. But here I've made some extra calculations by hand today. So V is this linear combination, which you see here. Psi is linear, then we come to this sum here. And then we have here especially this psi IB of the BB of this basis vector. And by definition, this is either 0 or 1 over B. So it is 0 if here is something missing. I need here that I is in B. So this is important here. Else the value is 0, and for I and B the value is 1 over B absolute value. So in this way now we come to the sum here. So now we can go on. We have seen this coefficient lambda B is equal to the coefficient lambda pi of B. So this gives the next equality. And now I can replace B by the new B will be the old pi up to minus 1 of B. So then I come here to this, instead of B to pi minus 1 of B, instead of pi of B to B. It's still the same sum. And yeah, this condition here can also be written in this way. It's still the same sum. And here we see that it's in the other value, psi upper B of pi of I of V. So it's the same formula as here upstairs. The first one is now here. This formula is the same one for the index pi of I instead of I. So I'm sorry for this mess with all these yellow colors. it's not nice. So this gives us the symmetry. Psi I, the entry at the index I is equal to the entry in the index pi of I for any I. Next, it satisfies axiom 2, the axiom of the dummy player. So we have given again the collision valuation, and now I is the dummy player of it, and we want to show that psi I b of v is equal to 0. So again, I write V as this linear combination of the new basis, sum of lambda b times vb. And now we use lemma 625d from the last video that said that all the coefficients lambda b are equal 0 if b contains the dummy player I. And now we have in the last slide, we had seen this formula here. And here we see the coefficients lambda b, but only for b with I element b, and they are all 0. Therefore, the result is 0. So the Shapley value has the entry 0 for any dummy player I. So the last axiom is the additivity. No, the last axiom is the first axiom, A1 is missing. It's the axiom of the effectivity, collective rationality, and the axiom of effectivity. So we want to show that the sum of all the entries of such a Shapley value at the collision valuation is equal to the collision value of the total collision. So we use again this formula which we had already proved, that psi I of v is equal to the sum here. Now here we have to add over all possible players I. Now we can rewrite this double sum by reorder the ingredients of this double sum. So we first sum now over the subsets B of A, and then we sum over the players I which are in B. So the summation here is the same as the summation here altogether. And we have the same summands here, lambda b times 1 over b absolute value. So, but now the sum over the I and b here is just, here we don't have I over b, the I doesn't turn up in the sum, so the sum of I over b gives just the factor b absolute value. That means that this factor then cancels, in this sum here cancels out. So this simplifies the sum. Then we come to the next sum, lambda b times 1. And yeah, 1 is the value of the total collision for any of these collision valuations vb. And now we are already finished. Here we have again this formula for v. This is equal to v. And so we get v of a. So we get the value of the total value, the collision value of the total collision A. So this finishes then the proof that the map psi upper B in part B satisfies all 4 axioms. Now we want to show that it's the only map which satisfies all 4 axioms. So we suppose that we have some map psi from the set of collision valuations to the vector space R up to M, which satisfies A1 and A2, A4. And we have to show now that this psi is equal to psi upper index B. So we want to test this now at the values of some special collision valuations. So let C be a non-empty subset of the player set A, and lambda be a real element, a real parameter. So what is the value of this map at the collision valuation lambda times VC? So, and we will calculate this, and from this we will get the answer that psi is equal to psi upper index B. So if I is in the complement of C, then I is a dummy player of the collision valuation VC and also of the collision valuation lambda times VC by lemma 625C, 625B. So the dummy players of the collision valuation VC are precisely the players in A minus C. So if I is in A minus C, then it's a dummy player, and then by axiom A2, psi I of lambda times Vc is equal to 0. The Shapley value of lambda times Vc vanishes on the dummy players. It vanishes at the indices of the dummy players. So these values are 0. Now suppose we have I element of C, and we have to see what is then psi I of lambda times Vc. So any permutation which maps the set C to itself is an automorphism of this collision valuation lambda times Vc. And therefore A3 shows that for any two indices I and j which are in C, the entries of the Shapley of this value psi are the same. So psi I is equal to psi j for ij and C. So they are all the same number. And finally, A1 gives us this axiom of effectivity or of collective rationality, gives us the value of lambda times Vc on A. Lambda times Vc on A is just lambda because Vc on A is equal to 1. So, and the axiom tells that it is equal to this sum here. Psi I of lambda times Vc. And so here we have the sum over all I and A, but those which are not in C, this sum vanishes, so we can stick to those in C. And these have all the same value because of the last statement here. And so the sum of their values is lambda, so a single value of them is here, just this value here, which you see here. Lambda divided by the number of the elements of C, that determines the values of this vector on the special collision valuation lambda times Vc. So, but this is exactly the value which our vector psi upper b has at the place I for this special collision valuation lambda times Vc. We had seen that we had defined that psi I of b of Vc is equal to 1 over C, absolute value, and the factor lambda is supposed to be linear, so we get the additional factor lambda. So then we find this equality here for any I. Yeah, and now the axiom of additivity tells us that these two maps are the same. So all the entries are the same for these special collision valuations. But any arbitrary collision valuation is a sum of such collision valuations lambda times Vc. So the lambda times Vc, any collision is not just a linear combination. Any is the sum of such collision valuations. And here it was important that I had some freedom in the choice of V. I hadn't fixed the lambda before, because I did not just want to consider linear combinations, but I really want to consider only arbitrary sums of these collision valuations. So by additivity, we get then that psi and psi upper b coincide on all collision valuations, so these maps are equal. So, and then this shows that psi upper index b is the unique map which satisfies A1 to A4, and because of that, A1 and to A4 have a unique map and unique solution, and this is in this map psi upper b. So psi upper b is equal to the psi Shapley. So this proves the parts A and B. Now I want to come to part C. Now I first show the statement. Here we have the statements of C, D, E, F. So part C was this explicit formula in terms of a weighted sum of differences of values of the collision valuation. So for a given collision valuation, the ith entry is a sum of differences for all the possible subsets B, V of B minus V of B minus I times a rational coefficient. So and now I want to prove that this formula is satisfied by that this formula gives us precisely the Shapley value for any fixed collision valuation. So here we are in part C. So I define a new map psi upper index C by the right hand side of the formula in C. This is again a map from the set of all collision valuations to the vector space R up to M. And now we will in fact not go into part B but into part A. We will check that this new map satisfies also the axioms A1 to A4, even A4 prime. And because of the uniqueness of the Shapley map, we then see that this new map psi upper index C is equal to the Shapley map psi Shapley. So we have to check that this formula gives us a map which satisfies all four axioms and even the linearity. So this map is a weighted sum of differences of values of the collision valuation on some sets times rational factors. And from the structure of the formula, it's clear that it's linear in the collision valuations. So therefore I just write OK. The structure of the formula tells immediately that this is linear in the collision valuations. So A4 and A4 prime are fine. A3. So A3 is this axiom of symmetry. So let us be given a collision valuation V and let pi, permutation pi, be an automorphism of the collision valuation and the cooperative gain. So now we go into the formula in part C. Instead of summing over all possible sets, it is sufficient. Yeah, one can also instead of summing over the sets B subset A, one can also sum over the sets pi of B, where B is subset A, because pi is a bijection. It's also on the bijection on the power set of A. So now we care about the entry of the vector psi C of V at the index pi of I. So we are here. We care about this, and we want to show that's equal to the entry of the same vector at the index I. That will give us the symmetry. So, but we start with the index pi of I, and so then we can sum over all B or over all pi of B. So we can sum over all B. And here instead of B, we can also consider pi of B, and here also pi of B. That doesn't matter. And also here pi of B, and then there also pi of B. That doesn't matter. But the pi here, that's different. That's an important part that comes from the pi of I here. So this is this first line here is now the formula for the entry psi upper index C pi of I of V. And now I make a calculation. Because pi is a symmetry, this whole difference is the same as this difference here. And pi of B has the same number of elements as B, so here the number is the same as this number, and also here this is again the same number. So, but this formula here is already, by definition, the value at the index I of psi of C of V. So it's the same formula. So this gives us the symmetry of this vector psi C of the given collision valuation under a symmetry of the collision valuation. So this was the axiom A3. Now axiom A2 of the dummy player. So again we have given a collision valuation, and now let I be a dummy player of the collision valuation. This implies especially that I doesn't matter for any coalition, so it has the same value with or without I, and this gives us then here that this vanishing of this difference here. And for any subset B which does not contain, the difference is 0 anyway, because we have the same sets on the left and right. So this tells us immediately that the sum here, the factor here is equal to the factor 0. So we have a sum of 0 times rational factors, which is altogether 0. So this is rather trivial. So this vector psi c of v has at the entry of this vector at an index I, which is a Shapley dummy player, is 0 by this calculation. So now A1 is more difficult. This is some longer calculation, and there is some diligent point, some difficult point. I will come to it in a moment. So axiom A1, we have to show that the sum of all the entries of this vector is equal to V of A. That's what we have to show, and we will get it at the end, but it's some work. So first we go into the formula. So this first equality is essentially just a definition where we have summed up over I and A additionally. So, and now here in this double sum, we can reorder the ingredients in this way. We can first add sum over all subsets B of A, and then sum over the players I which are contained in B. Yeah, and in the next equality, I somehow split this. I first look at this first factor with the rational coefficient, and then I look at the second factor with the rational coefficient. So, and the first factor with the rational coefficient is just this part here. This is easy. But the second part, that requires some additional thinking. Maybe first I erase this. This is too much. So, here I've prepared something. Upstairs we sum up over subsets B of A which contain I, but here somehow I sum only over certain subset C of A, and here I say I consider subset C equals B minus I. And I want to explain this in more detail, more carefully, and I've prepared something for this. Here it is. So upstairs in the formula we sum essentially over pairs B, I, such that B is a subset of A and I is an element of A such that I is in B. So we are now here. And I claim that this set is bijective to another set, to the set of pairs Ci, where C is again a subset of A and I is again an element of A, but now I is not in C. So this set here. And I claim that there's a canonical bijection. If I start with the pair Bi, I go over to the pair B minus I. And if I start with the pair Ci, I go over to the pair C union I. And indeed I get a one-to-one correspondence, a bijection between these two sets. And therefore I can now go into the sum, and the bijection will tell me that I can replace the sum here on the left-hand side here by the sum on the right-hand side. And here I have B minus I, and then here I have C. And these factors, I will see what it is. They will take care of it of themselves. And then the next step, I can also simplify the right-hand side formula, because the I here doesn't turn up in this sum here. Therefore, I just can drop this summation over I, not in C, and replace it by, and here's a mistake. So sorry, here's a mistake. This is not 1 over C absolute value, but this here is M minus c times this rest. So because the number of elements are not in C is m minus c. Here absolute value c. So, and this is used in the manuscript of the lecture course. So here now the sum over the second factor times this rational part here is equal to the sum of a c in A of v of c times this additional factor here times again this rational factor. So this m minus c is just what I had corrected on the other slide. So this is how this summation here is explained. So I wanted to be more explicit here about this summation sign. There was some work to do. Okay, and finally now, here in the upper sum I can put the absolute value b into this first factorial. Then I get b factorial times m minus b factorial divided by m factorial. And in the lower sum I can also put the m minus c absolute value c into this factorial. Then I get c absolute value c factorial and times m minus absolute value c factorial divided by m factorial. So I get almost the same summand in the two sums, but not completely. The summand where b is equal to a is missing in the second sum, because there for c equal to a, this factor m minus c gives me 0 here. And therefore this summand drops. Therefore in the difference, this summand precisely survives, and then we come to this summand here, and this is exactly v of a. So this was surprisingly difficult. I had to be very careful and creative in taking care of the summations here, but it works at the end of the day. So this then finished the proof of part C. It tells us that this map, which was given by the formula xi upper index C, satisfies the axioms A1 to A4, but from the parts A and B, from part A we know already that there's only a unique map, the Shapley map, which satisfies this axiom, so xi upper index C is equal to the Shapley map. So, and this finishes the proof of part C, and the other parts of the proof will be done in the next video. Thank you very much for your attention.